So welcome back, guys. So last time we started talking about split algorithms in section 3.4, and we already covered this part, which was about the Lagrangian and how we can add up the linear equations of our linear conditions ax equals b to the objective function using what we call the multipliers, the Lagrangian multipliers. And actually, we've solved an example where we had to go back and forth between the fact that the partial derivatives of L with respect to y should be zeros, and plug them back in the partial derivatives of L with respect to the x variables that should be equal to 0. And we already solved a problem, okay, for this. We already solved this case where we had to minimize 4x1 squared plus 2x1 x2 subject to 2x1 plus x2 equals 5 and x1 plus 2x2 is 4. So this is how the Lagrangian was written. So as you can see, this is f of x. And I here add up what? I here add up my Lagrangian multipliers multiplied by each of the corresponding linear equations. Okay. So of course, if you differentiate with respect to y, you will have the conditions, the linear conditions, and then you can solve, of course, your linear system in this case. Okay. And if you plug these x1 star, x2 stars in the derivatives of L with respect to the y's, you can get the values of the corresponding points. Okay. So this is what you should get. Hopefully, you verified this answer. So now, but I would like you to point something, to observe something. Now, can you say that this function here, this objective function, is it separable? Can you write it? So this is a function of two variables, x1 and x2. But can you write it as sum of two functions of x1 and x2? Is it possible?
For the minimization equation.
Okay. No, it's not related to the fact that it's minimization. Here, because you see there is a product here, you see in this case, 2x plus x2. Thank you, Khalid. 2x plus x2, you cannot separate it as a sum of two functions, as you see. So this function here, as you see, is not a function where you can write it as a sum of two separate functions of one single variable, x1 or x2. Okay? Why am I saying this? Because if you had a separable function, it would help a lot in defining the algorithm. And this is a very, very important thing we pinpoint, is that you should adapt this methodology to the problem you are solving, and not take any methodology and apply it blindly to any problem. Okay? Sometimes we see in some of the student papers, or sometimes also of the research papers we receive to review, is that they take, let's say, trending methodologies, highly trending methodologies, and try to, because they're using these buzzwords, and they try to apply them anywhere. But by definition, most methodologies are not defined, they need to satisfy, of course, to be applied to problems with some characteristics. Okay? And they may work wrongly on problems that do not satisfy these characteristics. Okay? So let us be very careful. And this is one of the cases that would happen, in fact, just in the next item. So in the next item, in fact, after we talked about the Lagrangian, we talked about the fact that, for example, from a broader point of view, in linear programming, we usually talk about primal and dual. And since here our problem was I think, a minimization problem, okay? And we said that in linear programming there is also a correspondence between what we call a primal and a dual. Okay? And these two problems are closely related to each other. In fact, when you solve one of them, you're solving its dual. Okay? And in fact, for example, if I take this small problem where I have to minimize, let me say, 3x1 plus 2y. So I'm taking just writing here just to plus x2, sorry. And just to notice the fact that it's very easy to write the dual problem. Probably you did that in any operations research course. And okay, so I'm saying this is my primal, for instance. Of course, we talk in linear programming, we talk about positive optimization. So our decision variables are supposed to be non-negative. So what is the dual here? The dual problem is going to be a maximization problem, where we inherit the coefficients in the objective from the right-hand side of the primal's conditions. So it's going to be, here in our case, 3y1 plus 4y2. So as you see, the b's which were in the primal right-hand side became the objective coefficients in the dual's objective. And here we're going to have y1 plus 2y2. So you see now, because as I said last time, it's yt a less than c in the condition of the dual. Okay? So it's going to be y1. So I'm taking it's just like taking the transpose of a. In fact, it's y1 plus 2y2 less than how much? And let you finish. You can say this. Less than 3, because I have to take this first objective inherited from the primal, and the next condition would be 4y1 plus how much?
Y2.
Y2, yeah. So I take the second column of A, I write it in line here, less than. Thank you, Khalid. And of course, here, this is the most simple case where we don't have equality conditions in the primal. So basically, the dual's variable would also be non-negative. Okay? In general, there is a general way to see this, and duality theory is huge, in fact. And basically, when we talk about continuous variable optimization, here we have no integrality condition. I mean, the decision variables are not supposed to be integers. It's very easy. It's common to define the dual and to work with this. Actually, even with integer variables, there is a way to define what we call kind of an approximated dual. But it's a research topic, which is quite intensive. We don't want to talk about it. Okay? So, in fact, this is inherited from from linear programming, and from a broader point of view, again, we can define what we call the dual of our problem here, which we said it is now what? It is a maximization problem. Maximize what? The dual function, which has the decision variables with respect to y, as we've seen. So we look for a point y star where all the partial derivatives are 0. So of course we are going to use the fact that our functions are differentiable. In other words, the gradient of m is equal to 0. So we take all partial derivatives with respect with the y variables. And the present problem has, in fact, a neat formula for those y derivatives that you should find. In fact, the gradient would be equal to ax star minus. Okay, so at the end of the day, what you need is to satisfy the later conditions. So if you are doing, in fact, an optimization, you are doing a gradient, not a gradient descent, a gradient uphill, or steep ascent. Okay? You might have heard about the gradient descent, which is generally used and very common in minimization. Now it's a gradient ascent. So one way to define the two steps of the algorithm, first of all, is to consider that the xk plus 1 to be updated is the solution of the minimization, okay, of lxyk. Argmin here means, what does it mean? It means that you're taking the x's that do minimize the L, using x's as variables, and the yk's here are fixed. constants when you start iteration k. Okay? Once you found the xk plus 1s from the minimization of the lxyk, you plug them in this formula to update the value of the gradient. So what you do, you multiply a xk plus 1 minus b, and you follow that trajectory, that direction, the direction pointed by the gradient. Okay? So if you follow this direction, what does it mean? You would be updating it, updating the y's, the dual variables here, or the primal variables in this case, because we are doing, in fact, the maximization. You update following that direction. Yk plus 1 would be equal to yk plus the step size to move in that direction, and thus in this improving direction. You get my point? Get it, guys? So this is how we work with the steepest ascent algorithm, not steepest descent, or gradient uphill. And of course, Sk could be adjusted depending on the case. There are ways to adjust. Type. Now I have a question. Why do we follow the gradient? You have seen this, I'm pretty sure, in previous mathematics course. And it's my pleasure to remind you this. Why am I looking in the direction of the gradient? Okay, I don't hear any answer. So let me remind you that you have probably taken calculus 3, right? Okay. In Math405 here at KFUPM or calculus 3, one of the sections, actually, this is section 14.6 or 0.7 in Stewart's calculus book. Okay, and Thomas calculus might be different. I'm sure it's a different section, but anyways, these are the most common used books in engineering. Whether you've taken it with Thomas calculus or Stewart calculus book, it doesn't matter. We've computed the directional derivatives, if you remember. What are the directional derivatives when you have a multi-variable function f? The directional derivative in the direction of a vector u is what? Is the gradient of f times the normed or unit norm vector u. It's just a dot product. You see? So in fact, what you have been doing in calculus 2.1, part of it is just basic linear algebra. And at the end of that section about directional derivatives, we show in fact that the gradient, in fact, is the one that is the gradient is the one that maximizes the directional derivative. Get my point, guys? The best vector to follow to maximize the directional derivative is in fact himself the gradient. Okay, so that's why it is called the gradient algorithm. Because you will follow the gradient to go in the best direction. That's it. And it has been already mathematically shown very easily in Math405. Okay? So just in case you wonder why we're doing this. So now let me move on to the new things. So now we're talking about the next split algorithm, which is a dual decomposition. So suppose that the original function f of x is separable. That's why I talked about separable functions. What does it mean? You can write it, which is here f multi-variable function. Here it's a kind of a capital X, where inside X I have all the n variables x1 to xn, and I can separate it. I'll give you an example in the next slide. The sum of n functions. In fact, those xi are subvectors of x, as it is explained here. So if you are able to do this partition, we can also partition the columns of A the same way and say we have n columns from A1 to AN. Of course, but what A I'm talking about? I'm talking about the linear system which is given the conditions here in the optimization. Okay? In fact, Lagrange's function here could be split in the dual decomposition in n simpler Lagrangians, we may call them, L1 to Ln. So for example, the Lagrange, which was written as f of x plus yt times ax minus b, could be equal to the sum from i equals 1 to n of the Li's. And each one here of the LIs contains what? It contains the corresponding LI with respect to the XI variable, and only the product of the YTs of the Y variables by the corresponding columns of the XIs. Okay? Of course, the remaining part is left to the step size to be taken care of. Okay? So now the X minimization of L splits into N minimization problems that could be solved in parallel. In fact, if you already did parallel programming, these problems could be solved in parallel, and you, in fact, instead of solving a huge problem that takes a lot of time, you can solve the whole problem in a much shorter time. So the two steps of the dual decomposition algorithm: first one, you find the xi k plus 1, which means the value of xi at the iteration k plus 1 would be the argmin, the one that minimizes the corresponding partial or Lagrangian LI. Of course, you should enter here with what? With a prefixed yk initially. I will show you in the next example. And then, once you find the xik plus 1s, you use them to update the a times xk. Okay, so you see the gap between ax and b, and how close you are to fitting the conditions, to satisfying the condition. Multiplied by step size, you should update the watts. And you go back and forth, and you see that you converge quite rapidly if you do satisfy the separability condition on the function f. Got it? So let's see it on the next example. Okay, here I'm citing some of the advantages or how you should proceed. So the n mu xi plus 1, in fact, gathered into a xk plus 1. Select them, and the resulting yk plus 1 is distributed to the n processors in parallel programming that execute separate minimizations in the next iteration. And of course, this can give an enormous saving compared to one large minimization when f of x is not set. And you see here, I'd like you to notice, especially the guys in computer engineering or computer science, how the progress in technology made us also come back with progresses in algorithmics and back and forth. If we were not able to have n processors in a workstation or a computer or server, we couldn't have been able to divide the problems on the different processors. Okay, so let's consider this problem, this example. Okay, where we do have. Okay, what do we have here? Do we have a separable function? 1 minus x1 squared plus 4 minus x2 squared. It's already separable, guys, right? So you can write it as you see here. 1 minus x squared, which is f1 of whom? f1 of x1. And the second thing, here you have f2 of x2, which is 4 minus x2 squared. Okay? Now, I'm adding the part y1 multiplied by the first condition plus y2 multiplied by the second condition. Got it? Okay. So let's start the algorithm. I'm here just starting with this routine 1.0. So I'm starting with the initial y variables be equal to y10 equals 1 and y20 equals 1. Okay? So what is the derivative of L1? How do we find it? In fact, L1 is what? Is the first function f1. So its derivative is the derivative of 1 minus 2x1, minus x1, 1 minus x1 squared. So it should be minus 2x1 plus what? Plus y1 from the first condition. Of course, initially should be 110 plus 2y20. Am I right? Because you get from here 2y20. So when you are at the point which is initially, this is the first step. At 1, 1 with 1, 1 with y1, 0 equals 1, y2, 0 equals 1. How much is this side? It's 3. So basically, the value derivative is this one, minus 2x1 plus 3, which needs to be equal to 0, which means you get x1, how much is it? x1, 1, how much is it? It's just 3 over 2, am I right? You find x1, 1 is 3 over 2. And for the dl2 over dx2, you'll find the derivative of 4 minus x2 squared. So dl2 over dx2, you'll find how much? Minus 2x2. And similarly, you'll find something which uses the y's. So it's going to be, can I write it here, plus 2y1 plus y2. So when you plug in y1 equals 1, y2 equals 1, you get 3 also. So you get also x2, 1 equals 3 over 2. Okay, so this is the first step. Okay? Now you take these values you just found and you plug them where? You plug them in the step size iteration or sub-iteration, where you write y k plus 1 equals yk plus s, the step, times x minus b. Okay? So of course, when you plug in these x's here, you can update the y's. So it's going to be no longer y1. For the next iteration, this is how the y's are updated. And you go back and solve again. So you see the x's will change. And at the end of the day, you should converge because you have this separability condition. It should work perfectly for you. Okay? You should try it. Here I just summarized to give you hints where you should go. Any question on this, guys? Nothing? Okay. So let me move on to the next. I don't know how to select here, but anyways, this is the last slide. It's not. Okay. The last slide here we have. Let's talk about an improvement of this, what we call the augmented Lagrangian. And in fact, this does not work well if the function is separable. You see, if someone loves now separability, well, the augmented Lagrangian is a problem. It's an improvement of the Lagrangian, but it's a problem for separable functions. Why? So to make the iterations more robust and help and converge if f of x is not strictly convex, we can augment f of x with a penalty term with a variable, let's call it rho. Okay? So as you see here, this is the regular Lagrangian, and we kind of added something that looks like the lasso optimization objective. So it's rho times the L2 norm of ax minus b. So I'm just like saying, look, my Lagrangian, get me faster to something very close to satisfying my condition. Okay? Because now the error here is multiplied to the power 2. Okay? So of course, if you start far from the feasibility, let's say, you get to add a huge penalty, which means you should be getting faster close to the feasibility region. Okay? So the same steps still lead to maximization, and the penalty constant rho here becomes, in fact, an appropriate step size S itself. Okay? But we can show that each new, in fact, xk plus 1, yk plus 1 satisfies that condition that the derivative of the L, in fact, is equal to 0. But there is a big drawback, which is what I'm talking about, the fact that you're trying to use methodology on a wrong problem, that adding this penalty term, which is rho, in fact, doesn't help with the separability. So the Lagrangian here, L rho, the augmented Lagrangian, is no longer separable. Even if fx originally was separable. Why is that happening to them? Even if f is separable, now the augmented Lagrangian is no longer separable. Why is that happening? because here of the augmented part here, because of the L2 norm to the square. Okay? If you put here the norm to the squared, of course you're going to have products of the x variables by each other. You can no longer separate your function into LIs, and that's why the problem is not settled. In that case, you need more and more steps to keep the advantage of separability. Okay? And next time, inshallah, we will start talking about the ADMM and further methods. Okay? Guys, do you have any question before we leave?
I just would like to ask about if there is any information about the project.
Okay. So let's start talking about the project.